Thank you very much. I'm going to share my screen here. There we go. Well, thank you everyone for joining us today for my presentation on structured cabling. It is making a comeback in the data center, and there are several important reasons behind that. Specifically, high-speed, low-latency communications in some of the functions that our data centers are supporting these days has become very, very important. So I wanted to take you through the reasons for that today. As mentioned earlier, I am giving this presentation today on behalf of the Communications Cable and Connectivity Association. We are a nonprofit association that's addressing quality and performance, but more importantly, safety, environmental impact, and other key issues regarding information communication technology infrastructure. Our members are made up of the leading manufacturers you can see here of cable and connectivity, as well as our distributors and material suppliers selling throughout the North America region. Our main focus is education and industry monitoring to ensure that all of the products used in very important communication infrastructure technology projects and installations are compliant to not only the performance standards, but also to safety standards that are in place in our marketplace. Let's start by looking at some of the latest technology trends that are taking place today. We know that the Internet of Things, or the industrial Internet of Things technologies is really taking off. There's a graph here showing the projection that by 2025, more than 75 billion connected devices will be in use in our world today. These devices are used to enable all of the services, technologies, and things we do on a day-to-day basis, and things that are coming down the road, like autonomous vehicle control, artificial intelligence, machine-to-machine communication. All of these things have become very, very important in today's world, and everything is running from or connected to some kind of data center. We also know that internet usage in the last 9 months has ticked up by 30% or more since the beginning of this pandemic. And we all know, you've experienced it as I have, remote work and remote learning is taking place, all of this enabled by a data center. Video streaming, online gaming, e-commerce, all of these things have increased significantly just in this year because of the restrictions that have been placed on us and the use of this technology that has enabled us to get by, to communicate with one another, to do our work, all through the use of this information communication technology that's funneled back through many, many data centers. And some of the other trends, like the rural broadband deployment, has become very, very important as we've moved to this online work environment, online learning. There's been a need to make sure that broadband is available even in rural areas. And the deployment of 5G technology has enabled a lot of new technology, or a lot of new services that are coming, and that 5G technology utilizes special data centers as well to be able to process all of the information that's coming from new devices that are being deployed out there. So the technology trends has started to translate to what the data centers really need to support all of these new applications and increased usage. We need more high performance virtualized servers. We need to be able to transfer traffic from areas that are overutilized to areas that are underutilized. And that means moving the function that's operating on one server to another server in the same data center, and sometimes in a different data center. So the bandwidth that we have both within a data center and between data centers is very important. And the latency that we have between various compute resources within a particular data center needs to decrease. We need lower latency for some of these very important applications. Faster switch to server connections. We're seeing that trend already take place, and I'll talk more about that in a minute. But we're also seeing a need for lower latency in server to server communications, being able to transfer those functions between servers. We need that to happen very, very quickly. We're also seeing higher uplink and backbone speeds taking place. I'll be mentioning 400 gigabits per second as one of the technologies that's been enabled recently, and that technology is here, and we're already looking beyond 400 gigabits per second for the next Ethernet speed. And finally, rapid expansion capabilities. You and I are utilizing Zoom today. If you've paid attention to the news lately, you know that Zoom technology and usage has gone up exponentially this year. They would not have been able to support that had they not been able to deploy quickly new resources, both in terms of compute, but also storage and just connection resources. And that expansion capability is very, very important. And we'll talk about how to enable that more in this presentation. So the traditional three-tier architecture that's been used for a number of years in the data center is depicted on the graphic on the left. This particular architecture generally emphasized the speed of connection in the north-south direction. So between my servers and my switches, or my access switch, and then between the access switch and my aggregation switch, those were the main concentration of, have we enabled the right amount of bandwidth? Do we have the right amount of speed? This particular configuration often used what we call a top of rack architecture, where those access switches were located in the top of every rack of servers. In this case, we're seeing that particular technology, that particular architecture was one that introduced a certain level of latency, and I'll get into this more later, where if you needed to have a application on one server in one of the cabinets be transferred to another server, you had to go through at least 3 hops from an access switch to an aggregation switch, back to an access switch, and then down to the next server. And that introduced a certain degree of latency. What we're seeing today is the introduction and usage of a newer full mesh leaf spine architecture. And that architecture has enabled what we call east-west traffic, or side-to-side traffic. It makes it much easier to transfer compute resources, information of storage between different devices at the lower level. So we're seeing every fabric switch or every leaf switch connected to every other leaf switch, as well as connected to every other router switch or spine switch. This has enabled some very low latency applications and has another number of benefits, as we'll see in this presentation. A lot of the leaf spine architecture, this virtualized architecture, has been enabled by the increase in fiber lane speeds. So we're all familiar with 10 gigabit per second lane speeds, which were the predominant port to switch speed for a long time. And now we're seeing the need to increase that server to switch speed, and it's being replaced, 10 gigabits per second is being replaced by 25, 50, and 100 gigabit per second lane speeds. This has been enabled by the introduction of a new encoding technology called pulse amplitude modulation, 4-level pulse amplitude modulation. So PAM4 encoding technology has made the switch from 10 gigabits really start to target going to 25, 50, and 100, rather than the old thinking going from 10 to 40 gigabits per second. Excuse me. 40 gig technology came out before the advent of PAM4 technology, and 40 gig was really the next logical step after 10 gigabit per second port speeds. Now we're seeing 25, 50, and even 100 gigabit per second port speeds start to be implemented in your switches and your servers. So switch to server links actually have already started migrating for several years now to 25 gigabit per second, with 40 gigabit per second switch to server links starting to be phased out. This is a server port shipment by speed study that was done by Del Oro, and you can see that the percent of the market that was represented by 10 gigabit Ethernet, even back 5 years ago, 4 years ago, was still pretty high, but you started to see in about 2015, 40 gigabit Ethernet switch or server ports start to take hold, and they were still going pretty strong in 2016. But in 2016, we started to see the emergence of 25 gigabit Ethernet, and it is starting to really take off in 2017 and 2018, and then the 50 gigabit Ethernet switch speed or server port speeds are starting to come into their own really in the last year, and 40 gigabit port speeds have really started to phase out in a big way. And there's specific reasons for this in terms of the technology used, the cost of the technology, and some of the flexibility that's offered by this PAM4 technology. Here are some of the standards that are enabling 25, 50, and 100 gig port speeds with single lane and some dual lane capabilities. With 25 gigabit speeds, you have 3 basic options for switch to server connections. You can use a passive copper direct attached assembly. So that's an SFP28 DAC. The issue, or not the issue, but that is a distance limited connection that is up to 5 meters. You do have both single mode and multi-mode options for connecting at 25 gig. OM4 fiber enables up to 100 meters, and single mode fiber certainly has the capability to go up to 10 kilometers. Similarly, you have similar options for 50 and 100 gigabit connections. Anything from 3 meters in a passive optical direct attach assembly to 2 kilometers for single mode fiber, and then options for multi-mode fiber as well. So these are all the different options you have, and often these types of connections, the choice of these types of connections will dictate what architecture you're using in your data center. So let's take a look at what the different options are and what your limitations and what the pros and cons are. Your direct attached copper assemblies are really limited in their distance capability, and so you would be using a top of rack architecture only with these types of connections. They're really only good for one generation or one speed. So in other words, you have a top of rack switch that has a 25 gigabit per second port, and that's going to connect to a 25 gigabit per second port in your server. If you upgrade either the switch or the server, you're going to have to upgrade both the switch and server ports, and you're going to have to change out the copper direct attach assembly to support the new application or the new speed. Often these are vendor specific, where you need to purchase the same manufacturer's switch and the same manufacturer's direct attach assembly for it to work together. They're not necessarily standards compliant. They can be proprietary. Because you're buying the same components from the same manufacturer, they can certainly be a proprietary configuration. And they often have a limited warranty in terms of the duration of the warranty. Another option for using optical fiber and getting a little bit longer reach is your active optical cables. Similar to a direct attached copper assembly, these would be good for one generation or one speed. You only have the ability to match port speeds directly between the switch port and the server port. These are optical assemblies that have the transceiver built into the ends of the connector, the ends of the pre-terminated assembly. Again, they don't have to necessarily be standards compliant. They can be proprietary. You're often, again, limited to using AOCs from the manufacturer of the switch so that they will be guaranteed to work together. Some of these are susceptible to damage during installation. So if you can imagine having the actual transceiver as you're pulling it through a cable tray and then getting to the other end, once you get that installed, there's no real way to test it unless you just plug it in between your switch and your server and you see if that connection actually works. So you can't put a tester on it necessarily very easily and try to test it to make sure it's not been damaged during installation. And often these, again, are associated with a very limited warranty because of the electronics built into them. The final option is using optical transceivers in your switch and server ports, and then using optical fiber structured cabling. Again, this has the capability of going all the way up to 10 kilometers, so it gives you much more flexibility in the reach that's supported. The fiber itself supports multiple generations of technology, so it can support anywhere from a 10 gigabit connection all the way up to a 400 gigabit connection. And that's whether you're using single mode fiber or multi-mode fiber. They are very much standards compliant. The optical cabling and the connectors need to be standards compliant, and you can easily test them. They're also interoperable. You don't have to use a single manufacturer's product. You can mix and match with those different products in your installation. And structured cabling generally has a 20 to 25-year warranty associated with it. And it doesn't need to be uninstalled or reinstalled anytime you upgrade your switch port speed or your switches and servers. So what are the hyperscale data centers doing today? What we've seen is that early adopters and the trend setters shaping our industry are very much in the process of installing 50 and even 100 gigabit per second server ports already in their data centers. And they're taking advantage of one of the things that the optical fiber structured cabling has to offer in terms of options for connecting switch ports to server ports. So if I have a switch that is, let's say, a 400 G-base SR8 switch, so that's a 400 gigabit connection that has 8 lanes of optical fiber in it. You can use a breakout assembly, as I've shown on the right-hand side here, that use an MTP with 8 lanes of, 16 fibers in it, and it's going to break it out to 8. It could break it out to 8 50 gigabit per second ports from that one switch port, or it could utilize 400 gigabit per second connections from that one switch port, or it could even support 200 gigabit connections from that one switch port. That for one 400 G-base SR8 switch port can support either 8 servers, 4 servers, or 2 servers. And you can mix and match, and you can change it at a later date without having to change anything more than this breakout assembly that you're showing here. All of the other structured cabling going between the cabinets where the servers are and the cabinet where the switch is would remain intact. So we're seeing a shift from the older top of rack configuration or architecture with the direct attach assemblies to an end of row configuration where you have optical fiber running between all the different cabinets in that same row to a switch in the end of, or in the middle of the row that's using transceivers to make all the connections to the other servers. Your AOCs or active optical cables, that 100-meter distance limitation may or may not be a problem depending on how big your data center is. But they do not offer the same flexibility in terms of being able to break out the number of active optical connections, do not have the option of breaking out the number of configurations that I just mentioned above. So what are the reasons that you would want to consider doing that and not top of rack? Well, in many cases, in top of rack configurations where you have a switch at the top of every single rack with all your servers in them, the extra switch to switch transmission between servers is, in different cabinets introduces latency. And that is going to become more difficult if you have an extremely virtualized distributed server environment. It's also more difficult to scale and manage. So you have these number of smaller switches to maintain in every cabinet rather than one server or switch to maintain in your end of row configuration. And you have to go to every single cabinet if you want to make specific changes on a specific server rather than being able to manage everything in a centralized patch field. Also, when you upgrade a switch in a single cabinet, you're only able to take advantage of that switch upgrade with the servers that are located in the same cabinet. None of the other switches in the other cabinets could take advantage of the upgraded switch at the top of that one rack in that one cabinet. There are times too where you're going to have poor switch port utilization. You may have a cabinet that doesn't have a fully populated cabinet that with all the servers that it could support. And so any of the ports that are not utilized in the top of rack switch in that cabinet are going to be sitting there kind of stranded. You can't really utilize them, and yet you're still paying for the full switch. So a good example of a top of rack configuration, or a diagram of that, would be what I'm showing here. And that shows that you have these top of rack leaf switches at the top of every rack or cabinet. And you can see that there are connections to the spine switches from each of the top of rack leaf switches, but you don't have direct connections between servers. So what that means is if I want to transfer the function of a virtual server from server A in the first cabinet to server B in the second cabinet, I've got to make a hop between 3 switches to get there. That introduces latency. Also, if I upgrade, again, the top of rack switch in one cabinet, the rest of the servers in the other cabinets can't take advantage of that upgraded speed in that one switch. And finally, I will have very poor utilization possibly in one of the top of rack switches if I don't have a fully populated rack, and the switch ports that are in that top of rack switch are underutilized and they're still consuming energy. So a lot of structured cabling is being reintroduced into these hyperconverged data centers. We're seeing low latency communication between any 2 servers in a row becoming very important in these virtualized environments, and clustering of resources becoming very important as well. It's a lot easier to scale and manage the changes in the data center. So you have one large switch in each row, whether it's in the middle of the row, the end of the row. When you upgrade that switch, you can actually take advantage of that with all of the connected servers in that entire row. I'm making all the changes at one patching location or one cross connect that's located either in the same cabinet as that end of row switch, or in a cabinet immediately adjacent to it that's dedicated to the patch fields. Any switch port can be connected to any server port at any time within the row. So you get better port utilization with the switches not being confined to any specific server cabinet. So this is what the structured cabling configuration would look like in that case. This represents all of the server cabinets with patch fields located at the top. All of those servers are connected with just patch cords to the patch field at the top of the cabinet, and that cabinet is then connected back to a patching area with structured cabling to the patch field that's located in the same cabinet as the end of row leaf switch. And therefore I can make a quick change in servers that I'm supporting with a specific application from A to B in a different cabinet very quickly, because I'm connected to the same end of row leaf switch. That really reduces the latency and very much enables that virtualized environment. Again, if I do the upgrade to my switch in that end of row cabinet, I now have the ability to support that higher speed in any of the ports and any of the servers in that entire row. None of the structured cabling that's been installed between the server cabinets and the patching area at the end of row cabinet needs to be changed. And finally, when I need to add another row or another cabinet in a row, it's very simple for me to do that. I just need to install the cabling back to the patching area, and now I'm able to take advantage of the other ports that are in that end of row leaf switch with all the servers I've just installed in that next cabinet, the newest cabinet there. This is what the cross connect might look like in the end of row cabinet. The top patch field represents all of the connections, all of the server ports are mirrored there in all of the cabinets. So each one of those rows in that vertical row, let's say in that patch field, could represent a different server in any one of the different cabinets. And the bottom patch panel represents all of the switch ports that are connected to that end of row switch. So when I need to make a connection between a switch port and a server port, it's a very simple patch cord in this one area. If I need to make a change from one switch port to a different server, I just quickly do that by utilizing the patching capability in that system. So I just move that patch cord without having to disturb any of the other connections in any of the other cabinets or having to go to any of the other cabinets. So when we look at the architecture in today's hyper-converged virtualized data center, what we're finding is, especially in areas where we want, where we have a co-location and we want to protect and give limited access to specific resources from the data center to our individual clients. What we have on the left side of this diagram represents the end of row server cabinet, where your connection between the servers and the switch at the end of row there is made. And we're using structured cabling back to a centralized cross connect that then is connected to your router switch and your core switch, which need to be maintained by the service provider, by the co-location provider, and not accessed by your client. Your client only has access to the connections between their fabric switch in the end of row and their individual servers, and all of the other connections are made in that main cross connect. So your hyper-converged virtualized data center now has the ability to basically protect access to some of the core functions that should not be accessed by the clients. So the key takeaway that I want to leave you with is that there's really not a single design for every data center. Certainly the three-tier architecture has worked for many years, especially for enterprise data centers that are supporting things that may not have latency sensitivity or high bandwidth needs. But the modern data center, especially some of your larger data centers and hyper-converged or hyperscale data centers, are benefiting now from the reintroduction of fiber structured cabling with cross connects. You can service multiple generations or multiple port speeds from 10 gigabits to 400 gigabits per second. You can support much larger range of reach depending on the size of your data center, or if you have multiple halls in a data center, I can move from one hall or connect from one hall to another utilizing optical fiber structured cabling, because I can support distances of up to 10 kilometers. Also, the latency considerations with this type of configuration, with a end of row configuration, are greatly reduced, which enhances the ability of a virtualized distributed server environment. And it enables keeping the leaf and spine switches separate and secure, so that you're not giving access to core data center infrastructure for other clients to a single client in a co-location environment. And finally, you get better port utilization and scalability by using a structured cabling architecture using end-of-row technologies. Of course, the cabling that you choose does matter, and this is why I'm presenting on behalf of CCCA today. There are the importance of using quality third-party tested fiber cabling and connectivity from reputable manufacturers. It can't be understated. You usually get better warranties and application performance insurance from manufacturers that have third-party testing from companies like ETL and UL. But what we've seen in the marketplace, and the reason that CCCA is here today, is that there are low-cost components from unproven sources that have proved to be very risky. We've seen the potential for counterfeit and other types of glass types out there that are wrong. In other words, you've ordered an OM4 multi-mode fiber, and what you get is not OM4 capability. So you're going to have some potential performance issues there. Or you have potential for an optical fiber that's supposed to be plenum rated when it's actually not plenum rated. There's things out there like subpar fiber end face geometry and poor mechanical reliability of the connectors themselves, especially with things like pre-terminated connector assemblies. We've seen those be available in the marketplace for very low cost, and they can pose an issue for the functionality of the data center. So our recommendation is that you look for reputable manufacturers like those that are members of our association. With that, I believe that I've used my time allotment, and I will open it up for a few questions.
Thank you very much, Todd. That was very, very interesting. It looks like we do have a few questions. This first one is coming from Dave Cadu. And the question is, do you see a significant transition by service providers to create more regional or local data centers to provide for better latency impacts as the residents' usage goes up due to working from home or schooling activities?
Well, we've certainly seen two trends. The deployment of additional resources within existing data centers, but in the deployment of 5G, the mobile network operators are starting to deploy specifically data centers designed to support this new technology. And these data centers are moving further and further from the core data centers, and they're creating what we call edge data centers to be able to handle some of the core compute functions that are going to be associated with very latency sensitive applications like autonomous vehicles and some of the other high-speed applications we're going to come to expect with 5G technology. So we have definitely seen that. I would say I'd love to go and talk to the people that are in charge of the Zoom data centers and to find out how much they had to expand their capabilities to be able to accommodate the huge increase in traffic that they're seeing.
Okay, very good. Todd, thank you again for a very interesting presentation. Looks like we're at the end of our time, so we're going to wrap this one up. And thanks for all the attendees out there who were able to join us. And hopefully this has been a good virtual IWCS for you.
Thank you.